Hi, thanks for joining this webinar. My name is Mike Zhu, an application engineer from United SiC. Today we will show you the breakthrough performance of United SiC's 750-volt Gen 4 silicon carbide FETs and how it enables a very simple and cost-effective design of highly efficient Totem PFC. 99.3% efficiency is measured on a 3.6 kilowatt demo board. We will introduce Fedjet Calculator, a very useful online tool that provides device selection guidance for various topologies with instant feedback of device losses, junction temperature, and so on. Finally, we will discuss a more cost-effective option of Totem PFC enabled by the Gen 4 silicon carbide FETs. PFC is required by international standard to improve reliability and efficiency of power grid. As the pace of electrification of everyday life accelerates, single-phase PFC gets more popular, and its efficiency becomes more important. We will first discuss the benefits of bridgeless Totem PFC and compare continuous conduction mode with critical conduction mode. Next, we will explain the great performance of Gen 4 silicon carbide FETs that enabled highly efficient CCM Totem PFC. We will show you measured efficiency and the power factor when slow leg is synchronous rectified. Then we will use Fedjet Calculator to understand the device losses. Based on the loss calculation, we will propose a more cost-effective design using diodes on the slow leg and still achieve above 99% peak efficiency. Finally, we will summarize the webinar and show you more interesting and useful contents on our website. First, from the principle of operation, we will discuss how Totem PFC provides higher efficiency, lower EMI, and simpler design if used in CCM. We will also compare CCM and CRM in terms of principle of operation, EMI, inductor design, and device selection. First, we will discuss why bridgeless Totem PFC is more efficient than conventional booster PFC. Left diagram is a conventional booster PFC with a diode rectifier bridge. Right diagram is a bridgeless Totem PFC. The name bridgeless comes from the elimination of a diode rectifier bridge. The efficiency improvement also comes from here. The arrows indicate current flow paths during positive half cycle of AC input. D1 and D4 always conducts current. Q1 is the active device. D5 is the freewheeling device. When Q1 turns on, PFC inductor L1 gets charged. When Q1 turns off, the charged energy in L1 now discharges through D5 to supply energy to the load. No matter Q1 turns on or off, there will always be 3 devices in the conduction path. Same for the negative half cycle. On the right, the Totem PFC has only 2 devices in the current conduction path. During the positive half cycle, Q4 will always be on, Q2 is the active device, Q1 is the freewheeling device. When Q2 turns on, the inductor gets charged through Q2 and Q4. When Q2 turns off, the inductor discharges through Q1 and Q4 and delivers energy to the load. During the negative half cycle, Q3 is always on and Q1, Q2 swaps their functionality. So Q1 and Q2 switches at high switching frequency, while Q3, Q4 switches only at line frequency. So we will call Q1, Q2 the fast leg, Q3, Q4 the slow leg. The diode rectifier bridge is replaced by Q3 and Q4 in Totem PFC. Since Totem PFC has only 2 devices in the conduction path, while conventional booster PFC has 3 devices, Totem PFC will be more efficient. Because slow leg Q3, Q4 only switches at line frequency, the DC output ground has low common mode EMI reference to the AC input compared to other bridgeless topologies. So now we understand why Totem PFC is more efficient from the topology operation. Next, we will discuss how to control it. Here we will compare the control methods CCM versus CRM. The left diagram shows continuous conduction mode CCM and the right diagram shows critical conduction mode CRM. Red curve is the average AC input current, black curve is the inductor current. From here we can see that one of the fundamental differences between CCM and CRM is the inductor current ripple. For CCM, the peak-to-peak current ripple is usually within 30% of the average current, while for critical conduction mode, the peak-to-peak current ripple is always 200%. Another fundamental difference is that CCM uses fixed switching frequency while critical conduction mode uses variable switching frequency. This is because CRM uses constant on-time to achieve power factor correction. From EMI point of view, CCM has less current ripple, and the CRM has higher turn-off current that could lead to fast slew rate related EMI. From inductor design, CRM requires less inductance to start with, but for high power, it requires interleaving that could lead to more cost, and with two inductors, the inductor size could eventually be similar. And the critical conduction mode requires high saturation current capability of the core material because the turn-off current is twice the average current. As to device selection, continuous conduction mode requires hard switching performance, which means the device has to have very good reverse recovery performance, which the Gen 4 silicon carbide FETs have, and we will show you in later slides. Critical conduction mode has soft turn on for the devices, but the turn off has twice the average current, so the turn off switching stress is still high, and it could have that fast slew rate related EMI. As to interleaving, generally, if one device per switch position can handle the power loss, in other words, if paralleling is not required by thermal dissipation, then without interleaving is more cost-effective and simpler. For high-power critical conduction mode PFC, interleaving is required to reduce current ripple to a manageable level. From previous slide, we know that Totem PFC is more efficient than conventional boosted PFC. Here we review the pros and cons of control measure, CCM versus CRM. Now let's apply CCM to the Totem PFC and discuss the benefits. On the left, we have critical conduction mode, conventional PFC interleaved for high power application. Its efficiency is limited by the front diode rectifier bridge, and total device count is 8. So this topology has low efficiency and high device count. In the middle is the critical conduction mode, Totem PFC, which gets rid of the diode rectifier bridge to enable high efficiency, but also requires interleaving to reduce current ripple at high power. Q1, Q2, Q3, Q4 are the fast leg, Q5, Q6 are the slow leg. This topology has high efficiency, but device count is 6 because of critical conduction mode and interleaving. On the right is the CCM Totem PFC that does not require interleaving. It has the high efficiency, lowest device count, low EMI, and therefore the simplest system here. From this comparison, we can see that CCM Totem PFC is an attractive solution for a single-phase PFC at high power. We have showed that CCM Totem PFC has simple structure and high efficiency, but CCM Totem PFC also requires very good reverse recovery performance from the fast-tech devices. So let's review the performance of United SiC Gen 4 devices and see how it enables this preferred CCM Totem PFC. The radar plot here compares the overall performance of Gen 4 silicon carbide FETs versus other silicon carbide MOSFETs. We can see that the Gen 4 devices provide superior performance for almost all key parameters in hard switching and soft switching figure of merits, while providing extra margin at 750 volt. In this radar plot, the smaller the area, the better the performance. The highlighted blue circle is United SiC 750 volt Gen 4 silicon carbide FETs. The gray circles represent 650 volt silicon carbide MOSFETs from 4 different vendors. We have much lower on resistance per unit area at both room temperature and 125 degrees C to deliver the lowest conduction loss for a given die size. We have lowest forward voltage drop on body diode to deliver low daytime loss and relieve the demand for synchronous rectification in third quadrant conduction. We also have lower hard and soft switching figure of merit to deliver lowest switching loss for both hard and soft switching applications. Please visit our website to discover more features of our GenFlow silicon carbide FETs. With higher voltage margin at 750 volt and superior figures of merits, GenFlow devices enable efficiency improvement, reliability improvement, and cost reduction for various applications including automotive, IT infrastructure, and renewables. Besides the great switching and conduction performance, the GenFlow devices also delivers gate drive flexibility. All devices can be safely driven with standard 0 to 12 volt or 0 to 15 volt gate drive voltage. Good threshold noise margin is maintained with a true 5 volt threshold voltage. Like previous generations, these new silicon carbide FETs can be operated from all typical silicon IGBT, silicon MOSFET, and silicon carbide MOSFET drive voltages. The VGS rating is compatible with silicon devices with a range of positive to negative 20 volt. It also includes a built-in ESD gate protection clamp that limits maximum gate spike within positive to negative 25 volt. As we discussed in previous slides, CCM Totem PFC requires very good hard switching performance for fast-lag devices. Here we expand the previous radar plot into two charts to focus on conduction and hard switching performance. Despite the increased voltage rating, GenFlow devices employ advanced cell density to reduce the on resistance per unit area, delivering the industry's lowest resistance products in all packages. In addition, the high current ratings are achieved by the device's advanced sinter die attach technology, offering improved thermal performance. Left chart shows the specific on-resistance comparison of 750 volt 18 milliohm device in 2247 3-lead and 4-lead package, and its closest 650 volt silicon carbide MOSFET counterparts. We can see that our on-resistance per unit area is 65 to 75% less at 25 degrees C and 45 to 70% less at 125 degrees C compared to its closest counterpart. This means for a given die size, we will have much lower conduction loss. Low on resistance per unit area also means for a given RDS(on), the device output capacitance is smaller and therefore reducing switching losses. The right chart shows hard switching figure of merit for the same 750 volt 18 milliohm device. It is almost 2 times better than the silicon carbide MOSFETs at 650 volt. From these two charts, we know that GenFlow silicon carbide FETs provides lower conduction loss and lower switching loss, making it ideal for the CCM Totem PFC. Now let's see how the GenFlow devices can enable a simple and high-efficient CCM Totem PFC on a 3.6 kilowatt demo board. For the demo board, we have single-phase AC input, 60 kHz fixed switching frequency. We will compare fast lag using two 750 volt 60 milliohm device in parallel with one 750 volt 18 milliohm device. The slow lag uses two 28 milliohm superjunction devices in parallel, and they are in synchronous rectification mode. Here is the top view of the demo board. We have the AC input and input filter, one DSP, PFC inductor and DC output. The right heatsink has four 28 milliohm superjunction devices as the slow leg in synchronous rectification mode. The left heatsink has two cases to compare. Four 60 milliohm device versus two 18 milliohm device as the fast leg. We will show you in later slides that one 18 milliohm device per fast leg position is better. Here shows the measured input waveforms. We have the input voltage, input current, and DC output voltage at high line and low line under full load. We can see that the power factor correction is well achieved, with the current following the voltage waveform. Let's also check the device switching waveforms. Here shows the turn on and turn off waveforms at low line under full load. The measurement is near the peak of the AC input voltage where the device switching current is also the highest. This means highest hard switching stress on the device. The left waveform shows turn on, the right waveform shows turn off. The purple waveform is the VDS, the blue waveform is the VGS. As we can see, the waveform for both VGS and VDS is very smooth and clean. Here shows VGS and VDS waveforms at high line under same load condition. Again, the waveforms are smooth and clean. The purple is VGS, the green is VDS. The peak VDS spike is only 470 volt, which is only 60% of the 750 volt device rating. The demo board input waveforms showed good power factor correction performance and very low EMI from device switching waveforms. Next, we will show the efficiency measurement. Left chart shows efficiency curve measured at both high line and low line for two 60 milliohms in parallel and one 80 milliohm device per switch position. The green curve shows using one 18 milliohm device at high line achieves a 99.37% peak efficiency. And the highline efficiency is always above 99% from 42 to 100% of the load. When two 60 milliohms are used in parallel, the efficiency is slightly lower at both highline and low line. So one 18 milliohm device is the preferred solution. We will provide detailed device loss analysis in later slides. The power factor chart is on the right. Power factor is near 1 when load is above 40%. Even at 20% of the load at high line, the power factor is above 0.96. So with this efficiency and power factor performance, designers can easily achieve 80 plus titanium standard. From previous slides, we have showed how the Gen 4 silicon carbide FETs can enable a highly efficient and simple design of CCM Totem PFC. Studying the device loss in details can provide even more insights on how to further improve the cost effectiveness. Fedjet Calculator is a great online tool to provide this information. Fedjet Calculator is an online tool that helps power designers evaluate United SiC devices in a variety of circuit topologies and quickly focus on the most promising solutions. It is easy to use and provides the data to make decisions very quickly and confidently. We have AC to DC, DC to DC non-isolated, and DC to DC isolated functions, and various topologies within these three functions. We also support CCM and CRM operation. In the results section, we provide efficiency, detailed component losses, including switching and conduction losses, device junction temperature, and effects of paralleling, and so on. And no registration is required, so very fast and easy to use. Please visit our website to check out. Here is a calculator interface for Totem PFC. To get here, we just need to first select AC-DC function, then select the topology, select the devices, and then enter your operation specs, and the results will instantly update in the right column. Here we would like to show you the accuracy of the Fedjet Calculator. The charts showed calculated and measured junction temperature of the 750 volt 18 milliohm device we used for the 3.6 kilowatt demo board at both highline and lowline. Yellow curve is the calculated TJ, blue curve is the measured TJ. We can see that the Fedjet Calculator results represent actual measurement very well, so designers can use the Fedjet Calculator to choose topology and devices with confidence. Now let's apply Fedjet Calculator to the 3.6 kilowatt Totem PFC. First, let's check the Highline with 230 volt AC input. The left chart shows device loss contribution per FET for the 750 volt 60 milliohm device. We have two 60 milliohm devices in parallel for each switch position, so a half bridge would require 4 devices. Yellow bar represents switching loss and blue bar represents conduction loss. At full load, the fast leg 4 devices would consume 16.8 watt. The right chart shows device loss per FET for the 750 volt 18 milliohm device. No parallel is needed here, so the total loss at full load is 15.6 watt. Clearly, the Fedjet Calculator also suggests that one 18 milliohm device is the preferred solution because it has higher efficiency and lower device count. This matches the efficiency measurement very well. In previous slides, when two 60 milliohm in parallel are used, it has slightly lower efficiency than using just one 18 milliohm device. Please also note that the loss per FET is so low with only 7.8 watts per FET. So smaller package and the surface mount package can be used to further reduce cost and the board size. Thanks to the superior on-resistance per unit area performance of the Gen 4 silicon carbide FETs, we can provide the 750 volt 18 milliohm device in TO220 and D2PAK7 lead package. Here we repeat the loss analysis using Fedjet Calculator again at low line. The 18 milliohm device is also more efficient than 260 milliohm device in parallel. Also, the 18 milliohm device provides very good balance between switching and conduction loss at full load, almost 50 to 50%. So with the help of Fedjet Calculator and experimental measurement, we get the same conclusion that the new Gen 4 750 volt 18 milliohm device is the right solution for the 3.6 kilowatt CCM Totem PFC. From the loss calculator, we understand that the loss per FET for the 18 milliohm is so low that a more cost-effective option becomes viable using silicon diodes on the slow leg and still achieves above 99% peak efficiency. The left circuit diagram is the CCM Totem PFC, and it includes the pre-charge surge diode D1 and D2. If we replace the silicon superjunction FET Q3 and Q4 with silicon diodes as shown in the right circuit diagram, we can have both cost reduction and size reduction. The pre-charge diode D1, D2 and slow leg diode D3, D4 can even use a single package as shown in the right bottom. Like we discussed before, if surface mount Gen 4 silicon carbide FETs are used for the fast leg, the overall device size reduction can be over 50% compared to the left circuit diagram. Here shows the measured efficiency with slow leg using superjunction body diodes. The green curve is the same as previous efficiency curve where the slow leg is synchronous rectified. The blue curve is with body diode. We can see that with cost and size reduction, we can still achieve above 99% efficiency from 50 to 75% of the load. This solution provides a good balance between efficiency and cost. To summarize this webinar, we reviewed that the CCM Totem PFC has high efficiency, low EMI, and simple structure compared to conventional interleaved boosted PFC. United SiC Gen 4 750 volt silicon carbide FETs provide superior performance in all key parameters for hard and soft switching applications. The Gen 4 performance enables 99.37% peak efficiency in a 3.6 kilowatt CCM Totem PFC. Such great performance even enables cost and size reduction and still achieves above 99% efficiency from 50 to 75% of the load. Besides this webinar, we have more contents on our website to help designers have a smooth evaluation of our FETs. We provide the following useful links as a reference. Easily driving higher power density explains our benefits from device structure point of view. Minimizing EMI and switching loss for silicon carbide FETs provides a better solution using simple RC snubber. In this webinar, we compared effectiveness and efficiency of snubber versus high gate resistance and explained why snubber is much better. We have dedicated web pages and videos to further explain the benefits of the new 750-volt Gen 4 silicon carbide FETs. Here are 4 application notes to help designers use our SPICE model for simulation and share tips that help control device switching speed. Please visit our website unitedsic.com to discover more interesting contents. Thank you very much for your attention. Hope you find this webinar interesting and useful. Please share if you have any questions.